So, good morning. Let me start. So, today's lecture is we continue where we left last time. So we are going more into the direction of the data light side of the knowledge graph for the course. So we have spent more than half of the course on the advanced architecture for deep learning, and now I started looking into methods that learn simple models, meaning that there are few tuning parameters, and in particular today I will go into the so-called physics / chemistry based or informed machine learning, artificial intelligence. So this is the plan for today. I will recapitulate points on sparse regression that I started introducing last time. Then I will go a little bit more in depth into symbolic inference. So genetic programming and a combination with sparse regression in order to learn a simple model from data. And then I will start talking about physics-informed machine learning. Okay, so last time I mentioned again, because this is more or less where we started the course, that we have machine learning class of algorithms where we learn a representation together with the predictive model. The most known scenario is deep learning, where each layer in the deep network is a representation, because that could be considered the input to the next part of the network, and in particular people look carefully into the penultimate layer before the output, because this is the kind of final representation, and then the network, particularly if it is a classifier, it is doing a linear classification on the basis of this deep representation. So then necessarily the network has learned how to map a complex nonlinear problem into a linear classification, of course through some nonlinear mapping. So an older actually kind of approach is symbolic inference that I started explaining last time, where we try to learn analytic equation that one can read and somewhat analyze. So in particular I would like to show how to bring together two fields, the field of sparse regression or compressed sensing on one side, and the field of symbolic regression on the other side. So this is a method that particularly has been developed in my group. There are some variants of this, not from my group, but it's just to show how different ideas could be combined in order to get better algorithms and more powerful kind of tools for data analysis. So the general idea of regression, before going to symbolic and sparse regression, is that we are aiming at a model class, that it is a linear combination, actually an affine transformation, because we include also the bias and this kind of representation. And we are looking for the vector or coefficient C such that you can map the descriptor into the property of choice. So we are looking for C such that we minimize the error that we do when we predict the known property from the input description. So for doing that we have to define a distance between the ground truth, P property, and the prediction, and this is in the forms of the typically, it doesn't have to be, but for regression kind of problem, it is typically a p norm, and actually most of the time it is a L2 norm, or p equal 2 norm, also known as the Euclidean norm. So it would be the sum of the squares of the component of the vector, and then you take the square root of that to define a norm, or sometimes you take it squared because yeah, it's handier for manipulation. Yeah, so you could have other kind of norms, notably p equal 1. You would have the sum of the absolute values, and then show in a second what are the implications of these norms, just not just the coefficient there, or so an exponent there, but it has implications. But before that, let me remind the kind of setup for the so-called compressed sensing. So the general idea is that we have a signal. Here is a time signal that could be first sight quite complex. So this is the blue line would be the kind of underlying signal that typically we don't know. We know samples of it, so the red dots. And so for this kind of signal, we know that the suitable basis set would be the Fourier basis set. So we have these periodic functions here, and we have to calculate the coefficients such that we can construct a signal. Now there are situations in which this signal is sparse. That means that basically it could be represented by only few of the basis functions, right? So in the example here, it would be that the signal is has only 3 frequencies switched on, and all the others are 0. So let's say that you construct the signal in such a way that it is just a superposition of 3 periodic functions, the cosine to just to make an example, with 3 different frequencies. And the task would be to find these 3 frequencies, to exactly which basis functions are active and which are inactive, by looking into the data with as few observations as possible, right? So in principle, not in principle, it can be shown that you can do this kind of reconstruction. So if the signal is sparse, you can find exactly the actual frequencies, the sparse set of frequencies exactly. For the sake of what I want to say here, it is interesting to show that what we are actually doing is to minimize the reconstruction error under the constraint that the number of vectors, components of the vector C is different from 0, is as small as possible. So let me elaborate a little bit on that, because the last time was left a little bit unspecified. So this formulation, so probably is better understood if we are saying that we are looking for a vector C. Just checking to use the same notation. So we are minimizing. So this would be compressed sensing. Let me write it clear. What we are actually doing, what we would like to do, is to minimize with respect to the coefficient C this norm, subject to, so the strong formulation would be that we impose that P equal DC, so that the error is actually 0. Now, in practice, that would be some noise. So that in practice we are minimizing as smaller than a certain threshold level, right? So this would be a 2 norm. So it is the kind of distance, the error squared between the signal and its reconstruction. So, and this zero norm is the number of non-zero coefficients in C. And this can be understood by looking at the trends of these norms. If we look at the circle or the sphere for the different p norms, so let's say we have let me just use the same notation. Right, so when p equal 2, we would have should be able to move this a bit. Okay. Anyway, so this would be situation for p equal 2, and the p equal 1 sphere into dimension would be this one. And if we go for p that is smaller than 1, we would find that we get this kind of non-convex construction here. So these points are all at the same value, could be 1. I mean, we scale so that we have the spheres of radius 1, and so this would be, say, 1/2. So now if we take the limit for p that goes to 0, we would basically get something that collapses to these deltas on the axis, that essentially would be counting how many of the coefficients are different from 0 for any given vector. Okay. Yes. So now we one can prove that with some on D, the matrix D here, we can solve this problem by minimizing this similar expression. So we are looking for the 1 norm subject to, again, that p minus dc is smaller than a certain epsilon, right? So this is not trivial, but one can show that if the matrix D has, say, uncorrelated columns or rows, actually the right word is incoherent, then we can essentially map this minimization problem, the L0 one, into the L1 here. So we are looking for solutions, so we want to minimize this, and at the same time we want to minimize this. And so also one can prove that in this situation there exists a lambda bigger than 0 such that the solution of this problem is the same solution as the problem minimization of say P minus DC square, say typically this written in this way. What we are minimizing is the error. And then we have the so-called regularized minimization, right? So we have the lambda that goes here, it is bigger than 0, and you see the say same components of the previous problem are there, but they are combined in one expression. So instead of having this constrained optimization, we have a kind of relaxed form of the so softened kind of form in which we are trying to minimize the two things at the same time. So with a little bit of abuse of notation, we basically can write back a similar expression also for the L0 problem. That is what we are actually trying to find, even though the correct formulation would rather be this one. So this one that I've shown here, and is used often in literature, is a slight abuse of notation, but it describes exactly the same situation. So this is what I just said, that the zero norm would be the limit of this P norm going to 0. Yeah, it is worth mentioning that when we go for P smaller than 1, these norms are not really norms. They are called quasi-norms because they lose the triangular kind of inequality. So, but I will skip this level of detail. Now, yes, so as I was just saying, one can show that a solution of this problem would be this one. That is, so this one is done with some kind of iterative descent in order to find C, but this is a convex problem. Well, this is not necessarily a convex problem. So with some constraint on the matrix D that actually, as I will show, it is not often easy to satisfy, and so we need other ways to approximate the solution. And as I mentioned last time, so we go over all this trouble here because the problem as stated here, or better as stated here, can be shown to be NP hard. So basically, so this problem is NP hard. That in practice means that the algorithm for the exact solution goes by enumeration of an exponentially large amount of candidates, basically looking at the one component different from 0, two component different from 0, enumerate them all, and then find which one minimize the overall problem. So we look for ways to solve the same problem in a more efficient way, or in a feasible way, because an NP hard means that sometimes, so very, very quickly we exhaust resources to actually solve it. Okay, so this is what I showed already last time, and briefly now sketched on the whiteboard how these norms work. And then this is a correction with respect to last time, as I suspected, so I checked the original sources. The recovery of the signal is possible when the number of observations is larger then something that goes linear with the sparsity, and with the logarithm of the number of features. So the big thing is that we can address situations where we have a very large number of features with relatively few observations for moderate level of sparsity. So this is the message from this compressed sensing, where we can do this kind of analysis. We can look for a solution that looks otherwise a little bit desperate if the signal was not sparse. And then very briefly, I just remind the kind of classification of methods for feature selection versus extraction that I made last time. So basically, we have methods for feature selections, and we are looking essentially now in these wrappers kind of things. Yeah, so the kind of naive way to do is to kind of iteratively subtract or extract, select variables with some kind of iterative methods. Then you would have these wrappers. I will explain in a second the genetic algorithm here. And then we have things like lasso, the L1, kind of recasting of the compressed sensing problem that kind of embeds the feature selection. And so this has to be distinguished, even though in English sometimes, so in English they have a very similar meaning, and I already just used wrongly extraction once. So in machine learning, feature extraction is rather a combination of the existing features. So we don't necessarily reduce the number of features. We reduce the dimensionality of the representation, but the features could depend on all the original feature. So the typical thing is, say, principal component analysis, route encoders, in which you have a lower dimensional representation, but not necessarily we select from the features that are given up front. So now switch to the genetic algorithm part that then we unify with the sparse regression kind of approach. So the general idea of genetic algorithm is that we can represent, so we have a population of individuals, and we want to find the fittest individual with respect to some defined fit function. So it's called evolutionary genetic because it shares ideas with the Darwinian kind of evolution. Or it's kind of the mathematical representation of Darwinian evolution. So what are the individuals? So the individuals can be anything. Could be molecules, materials, could be people, and we represent their characteristics. So basically points in some representation space. Say with a binary encoding, so here it doesn't represent necessarily anything in particular, so just a string that has a representation, but we can go from the string to its fit, right? So we define in some way that this is the fittest we have seen so far, and this is the least fit that we have seen so far. And the idea of genetic algorithm is that we want to find the strings that are even better than the best that we know so far, and to do that we basically select some of the fittest that we have at the moment, and then we do an operation that again justifying the genetic algorithm kind of label. It borrows from genetics, so we do a crossover. So we cut the string at some point, and then we kind of merge or recombine by swapping the kind of substrings. And then we also consider a mutation kind of operator in which we say, okay, now the the result of the crossover string will get some kind of random flipping here in this binary representation, right? So we would have this thing, and then we evaluate the ranking of these new functions. So the idea is that if so by using some parts of the representation for the best individuals that we have seen so far, and we combine these features, we can get better than where we are, right? So, and we stop the algorithm when we have a fit function that we could be happy with. And to make an example, so the genetic algorithm has been used a lot for different kind of applications, including proof of theorems, for example. It is worth mentioning that it has been also used for the global optimization of atomic structures, with the idea that you start from molecules or clusters, so generally represented as a sphere here, and your crossover operator would be cutting randomly the molecules and then combining half of the molecules in this way. So of course in the practical implementation one has to deal with two short bonds that would appear at the interface between the two half of the molecules. But other than that, this is the general gist of the algorithm when we want to use genetic algorithm for the global optimization of molecular atomic kind of structures. So atomic structures, be it molecules or clusters, in principle solids, a little bit even more cumbersome because of the periodicity that has to be respected when you recombine the molecules. Subsets of atoms. Now we borrow this idea with the, so I haven't introduced yet, sorry, so this would be our model where we use ideas from genetic algorithm to do sparse regression. Right, so this would be this kind of merging of symbolic regression with sparse regression. So here we move in the space of features, and we construct a combination of features, nonlinear combination of features, by borrowing from this genetic algorithm idea. So genetic programming, to be more clear. So basically we say, okay, we have features, and then in general could be that they have dimension of length, of energy, some of them are constants, and then we combine them, right? So we start applying some operators like a sum, difference, absolute value of the difference, define other operators, vocabulary of possible operators that we apply. And the nice thing is that, and this is why I started constructing this kind of tree-like structures, is that if we can express formulas like this one in terms of a tree. So we have this ratio of difference of energies divided by some sum of lengths is so operator ratio, an operator sum and difference, and then the leaves are the features themselves. And then, all right, so another example, this would be the representation of exponential of minus some ratio of lengths. And interestingly, we can basically, substitute. So we take a subtree, and then we substitute a subtree like this one, and we still get an expression that it is well formed. So what we are going to do is to find an expression like this one that minimizes the reconstruction error. So what we do in this combination of evolutionary programming or genetic programming with sparse regression is that we construct these trees, and then we exploit the fact that so look that this symbolic tree are slightly different. So ratio is a sum, and then logarithm of the ratio and exponential of minus the ratio, and then we cut at some point like here and there, and then we basically can combine the two expressions, like including this logarithm of exponential, where you would need then when you code that some interpreter understand that these things is actually the absolute value of minus x. So this symbolic approach and construction of trees for constructing more and more expression with using crossover. The mutation will be, of course, changing a feature or changing an operator randomly, right? And this gives us the possibility to construct this expression, and then we check the fit of this expression. Sorry, it is written here. I was looking for this expression where we want to minimize this error, right? So we look for the tree or expression that would kind of minimize this reconstruction error. And so in the practice, so we could construct trees at very different depths, right? So we keep on iterating this kind of construction until we get construction of a certain complexity, and typically the more the complexity, the lower will be the error. So it turns, I mean, the larger the complexity, so the depth of the tree, and so the number of operations that we do with different features, so we will reach expressions. Some of them will have a lower error, reconstruction error. And now we have this kind of situations in which we may have features, so expression with different complexity and different reconstruction error. We want to decide what is the best. So we have basically two independent parameters: the complexity and the reconstruction error. So the accuracy, let's say. And then we want to rationalize what we want to look for, right? So here invoke the concept of Pareto optimization, that it is the typical multitask, multi-objective optimization scenario, in which we have many things to optimize at the same time. And let me introduce the concept of the Pareto front. So basically, if you have a measurement in which you measure two objectives, then they will kind of arrange in some area of the objective 1, objective 2 kind of diagram, and there will be a set of points such that no point have simultaneously better objective 1 and objective 2. So this could be also for many dimensions. It's just difficult to represent. So you can well define in n dimension points that for which we don't have points in our populations, so that you simultaneously optimize object. So you improve on them on all the objects at the same time. So to fix the idea here, okay, take any point like this one. So you don't have a point. So you can have points where objective 1 is larger, like here, but then objective 2 would be smaller, and then vice versa. You would have points in which objective 2 is larger than that, but objective 2 is smaller. So there is no point outside this front, and this is called the Pareto front. So these are all the optimal solution for our problem. Which one we want to choose now depends on other considerations, right? If it is more important that objective 1 is smaller, or objective 2 is smaller, or some other considerations that lead us to a final choice. But these are all optimal with respect to the multi-objective kind of optimization. And so let's say that, Okay, this is in word what I have just said. And let's say recast into our genetic programming, evolutionary programming kind of problem. We say, yeah, that's why I had the axis in the weird orientation. So we want to optimize, so have the largest possible accuracy, at the same time the lowest possible complexity, right? So this is a minimization in this direction. And so this would be our Pareto front in a kind of a generic scenario, and we want, so each of these points would be interesting. So let me now just show how this set of ideas has been actually used in practice in a kind of a landmark paper in 2009, where people were using this kind of approach, evolutionary programming, to find equations that describe physical systems. So just to fix the ideas, what they really looked, one of the problems they looked at that into the paper. So what they present is this kind of double spring situations, double oscillator, that was actually realized experimentally. So they were measuring experimentally the position x0 of a certain mass, and then they had this time series, right? So this would be the position and the velocity. This is what they would measure, and then the algorithm, a genetic algorithm where expression were constructed, found essentially the equation of motion of this. Actually, here what this is shown is that it found also the constant of the motion that we would call the Hamiltonian, right? So basically, it finds kind of balancing between the kinetic and the potential energy that we would be able to do it from physics, but here it was reconstructed by constructing this expression in a systematic way and using the actual data as input. So this is a little bit messy, sorry, but so this would be exactly the Pareto front that they would kind of look into. This actually is a second kind of application that they had in the paper. It's a double pendulum, and they had kind of different solutions. So they have the predictive ability. This goes minus log of the error, so the larger, so closer to zero, the more predictive, so the more accurate. And then they have the something that goes as the number of nodes in the tree. So they call it parsimony. So they want to optimize parsimony. So then it's like this would be the Pareto front, and then each solution there would be worth considering. And then we yeah. So this would be an expression that the algorithm finds. So it is worth saying that in principle, not in principle, if the exact equation that governs the data is within the reach of the algorithm, it will be found, right? So because at some point, imagine that there is no noise and you have generated the data from some given equation, so you simulate them, and then it will be possible to reconstruct exactly what was the input, and find the exact equation if the complexity of the tree could reach the exact equation. So for other methods, this is so the kind of universal approximator. This is not the case. So you will not. You can systematically reduce the reconstruction error, but you do not necessarily reach the exact expression that has generated the data, right? So it will be an approximation to that. And then the fact that you have a few fitting parameters. Yeah, here it would be, in this expression would be the case, for example, and while the omegas and the theta are the variables. So basically this leads to robustness with respect to noise, right? So if the exact equation and you have noiseless data, it will be kind of simulation scenario. In a realistic scenario, there will be some measurement noise, and then we would find an approximation, the best approximation, and in this kind of setup, the fact that we have few parameters kind of enforce stability in the inferred model. Okay, so now going to the actual merging of the two fields into a method for learning equations that we call this sure independence screening and sparsifying operator, the SISO. So again, to restate the problem, we are saying that we are expressing a property as a linear combination over nonlinear functions, and we want to have as few as possible of these coefficients different from 0, and at the same time we want to have a richness in the creation of the nonlinear functions, so we construct them systematically, and we then select which of them, and to give numbers, so P is the vector of observation, so as many components as the number of data points, training data points. So then the basis function will have the same number of components, but the number of this basis function could be, and it is typically much larger than the number of data points. So we are immediately recast into the compressed sensing scenario, in which we want to reconstruct a sparse signal, because we assume that there are only few basis functions that are active. So it is worth noticing that this kind of problems is known in the field, so one approach is to use the so-called orthogonal matching pursuit, that is a so-called greedy method, in the class of greedy methods. So the idea is that okay, so you have this expansion, you would look for the first component that maximally correlate with the property, right? So these are vectors, so you just kind of find the one that has the smallest scalar product with respect to the property, with kind of learnable coefficient C1, and then this is fixed at this point, so this where is the greediness, so you find the first component, and then you look for the D2 that would minimize the what is left as not explained by D1. So the point is that yeah, if you do like that, even this very simple scenario, there could be a D1 star such that there is a D2 star together will make a better prediction than the D1 and D2 selected in this greedy way. So because you don't go back and analyze if there were other D1s that combined with some of the residuals would give a better prediction. So this is where we enter. So this would be the method that we have introduced a few years ago, where we actually select a bunch of features that correlate with the property. So not just the best one, but a certain number. So how many? That's a hyperparameter to be optimized. So say to fix the ideas could be 10, 50, and then we proceed, and for each of them we calculate the residual, and then we look for features that correlate with this residual. So we keep the overall number of features that correlate with the residual small, right? So otherwise it becomes again combinatorial, because we do that iteratively. And so before going on what we do after this selection, let me talk about this similarity. So we select features that are correlated with the property. So we could have the Pearson correlation, so just the scalar product. But sometimes it is also useful to use other metrics, like there is a so-called Spearman correlation, for example, that could capture nonlinear nonlinear kind of correlations, some nonlinear correlations between the property and the feature. So we could use other methods to do this kind of screening. So this is a sure independent screening part. So why this sure independent screening? So the idea, so the name is a little bit cryptic, but the idea is that if you increase the number of features that you select at this step, at each of the step, you are guaranteed to find the optimal solution, right? So it would be of very little use because it becomes again a kind of combinatorial kind of search, but it's just a guarantee that you have only one control parameter where you cut the number of features, and then if you increase that, you will reconstruct the exact signal, the exact signal. Now, after the selection, we do what we call the sparsifying operator. So we do the actual L0 minimization, but now on a subset of features. So as they say, we started from a huge number to give numbers that we actually treat billions or trillions even. So 10 to the 9, 10 to the 12 features. So with a number of columns in the D matrix, right? And then we like to do that with few observations. By few, I mean really 100 to say a number, not 10,000 or 100,000 or a million like we could have for deep learning models. Not necessarily, but that's the kind of typical scenario that you would find in modern deep learning trainings. So basically we have this selected subsets, and we then construct the union of this subset, and within this overall set of features that have been selected from the given ones, we look for the one that minimizes this error. So taking into account the penalty on the number of coefficients that are different from 0. So we basically do the enumeration, but on a subset of features that have been selected in a smart way, with this kind of guarantee that if you select, if you essentially do not select, you find the solution, the full solution. But in this way, you find a good proxy. So this would be the algorithm in practice. So you start from a set that is empty, and then you rank them according to the similarity to the residual, add the selected feature to the set of features, and then you do the least square regression on the selected features, and the lowest will give the model with that number of selected features, right? So because we are at the iteration here goes with the dimensionality here, and then we stop when we are happy about the error. So to fix the idea, this was the first application that we did, just to see how we construct the features. So we wanted to kind of see if given octet binary chemical formulas, if they would crystallize as rock salt or zinc blend. So actually, to recast it into a regression problem, so we have a counterpart that is a classification, but we wanted to say, okay, let's look at the difference between the two. So the sign of the difference would be the classification, but then we also introduce a little bit more semantics, because basically we distinguish between materials that are almost zero difference between the two, and those that are very different energy between the rock salt and zinc blend. And the input features, what we call the primary features, would be, say, some atomic features, for example, atomic level, Conshan levels, in this case, for the isolated atoms, or the extension of the radii. So you calculate the area distribution function for the orbitals, say some valence S or valence P orbital for the elements, and then you take for example, the radius at which this distribution is maximum, so the mode, or the average, some expression of the extension of the orbitals, and then we combine them. So this would be some this radii or some condition level, and then we combine them, and then each of them would be a column in this representation, and we are looking for the few that are different from 0, so that we actually use them. So this would be the actual solution that was found. So we have this descriptor. It depends on ionization potential, electron affinity, this p radii, and s radii, and then well, okay, of course the ionization potential, electron affinity are related to the condition levels. Yeah, I should have put it here, but okay. So these are numbers that you get from the atoms, and then you get essentially an expression also for the dividing line, so for which the difference is 0. So on this side you would have rock salt, on this side you have the zinc blend, here would be carbon diamond, so the one for which the difference between rock salt and zinc blend is the largest, kind of on the zinc blend side, and then this is what we found. So we boil it down to a two-dimensional map, and then we have a predictive model for the difference in energy between the two. So to close this CISO survey, it's very important noticing that we can fix the complexity as hyperparameters, right? So basically the number of non-zero features, so this L0 norm is one parameter, and the complexity of the kind of symbolic tree would be another parameter, right? So comment here. So you would have expression that have two levels in the tree, right? So one is making the sum and difference, and the next level would take the ratio, or here would be the product of sums. And then more levels would be, okay, first you take the square, and then you sum, and then you do the ratio, and then you see these are more complex expression. And so here you would have the validation error, so the error that you do on data that you have not used for training, and then it would kind of decrease with the number of dimension unless it becomes too many parameters, so you start overfitting. Here you see a signature of overfitting, but in general, so you stop somewhere here, say 3 dimensions, and the absolute error is still decreasing with the complexity. Yeah. So this is not the same example as the bi-octet binary. It's another kind of application, but just to show a real life scenario in which we tune the level of sparsity, so how many coefficients so how many basis functions you switch on, and then the complexity of the feature space. Okay. So yeah, to summarize the CISO kind of idea, we have a regularized regression that is constructed to do massive classification. So you go from billions, trillions of features in the column of the matrix D to 2, 4. We had the sample with 6, 7, but hardly more than that. It is a dimensionality reduction because we go from this super large representation to a small representation that it is supervised, so it's not like PCA that is an unsupervised dimensional reduction. We do feature selection with a non-greedy solver, and then it's really a symbolic regression, but instead of doing it randomly as with the genetic algorithm, so stochastically as with the genetic algorithm, we do it deterministically, and we always find the same solution from the same input data. I introduced at the beginning my friend the platypus to just say, okay, here we are an intersection of many different classifications, so there is a very blurred boundary between these kind of classifications. Okay, and to close this discussion, before I go to the physics informed machine learning, I want to give a quick overview of the point of interpretability of these models. I will try to have a full lecture on interpretability and the kind of interesting counterpart for physics, that is the causality. So just to make the point that so this is taken directly from a kind of one of the reference books for say statistical learning, machine learning. So a book from James Witt and Hasti Tibshirani. So Tibshirani is the famous statistician that kind of among the many things he introduced the L1 kind of regularization, so this so-called lasso, and so this is a very highly regarded book, and there essentially they define the interpretability as that thing that so they never define it in this way, but it boils down to interpretable is a model that is linear with few features, right? So then this lasso approach and related, so this CISO that I just mentioned are interpretable because they basically boil down to a linear combination of input features, right? So and then the more you make complex the class of functions that you're using for, so the model class that you're using for doing your modeling, where the most complex would be neural networks. So you lose interpretability, and this kind of anti-correlation is kind of built in, right? So as we will see. There is a different word that people use about neural network that is more explainability when they want to understand what's going on. So I will come back to this kind of concept just to say that often there is difficulty in communication when saying that a model is interpretable, because so one can load this with expectation on the physical kind of meaningfulness of a certain model, while from a statistical point of view the interpretability is needs just that you have a sparse, so a linear and sparse representation. So I will come back to this point. So this would be it. Yeah. So it is very important to notice that a simple model could be very accurate, because if the exact model is reachable, it will be found, so it will overperform over kind of universal approximators. Okay, I think the presentation here is stopped, so and let me go now to the next part of the lecture, that is physics informed machine learning, or artificial intelligence sometimes. So as for interpretability, where we'll come back, this is a field that is not very well defined, so it's more a set of ideas and concepts, and unfortunately the literature is already in some mild disagreement, so I will try to systematize a little bit. So let me first try to not define, but kind of give some kind of expectation list what we mean by a model that has that is physically informed. So basically, when we treat a problem from a physical point of view, so we analyze observational data on nature in some sense, and then we have a physical modeling interpretation of this observation. We aim at explanations, modeling that are, well, again, this word, interpretable. Arithmetics means that we can relate some kind of variables to other variables, so the kind of input variables to control the phenomenon with respect to what we observe. So if we have a pendulum with a certain initial angle and with a given mass, then we can predict its motion, given some other assumptions. And so, yes, we want the model to be generalizable, where the physical generalizability is a kind of quite strong request that we do to the modeling, right? So we know kind of the famous kind of generalization wonders of physics, where say Newton was modeling the fall of objects to the ground, and then he said, okay, if it is exactly the same mechanism that governs the motion of the moon around the Earth, so that was the assumption, and then he found out that yes, he could explain the motion of the moon around the Earth as essentially the moon falling to the Earth, but with a certain tangential component of the velocity such that it always fall beyond the horizon, like, so it would be like having a falling object that is tossed with a certain component parallel to the ground that is such that it always fall beyond the horizon, so it orbits. So orbiting and falling are two related concepts, and so you can generalize the law of motion and the description of motion of falling objects to kind of orbiting objects, and then further, right? So if Newton gravitation kind of works for the orbits, then there is a problem when you look at the moons of Jupiter, because the kind of appearance time, so the period that you would observe, seems to be wrong with respect to the prediction if Newton's law were applied to the observation themselves. And then you say, okay, if I believe in Newton's laws in the sense of physical generalizability, they say, okay, let's hold that they work and not believe in any other sense. What else could be different? Could be an explanation why the orbital period of the Jupiter moons is not what we expect when we look from Earth. Okay, you know probably what was the point. So the strong hypothesis here would be, okay, what if the observation itself needs time to reach us, so there is a finiteness of the speed of light, and then indeed, if you take into account the finiteness of speed of light, Newton gravitation works, and you get as a side effect that you can measure the speed of light actually. So you see, this is kind of the power of generalizability. Then you have other famous examples like again gravitation, but now Einstein's general theory of relativity, in which you say, okay, I introduce much more complication. Let's say that happens to explain certain irregularities in the orbit of Mercury, but it comes with a very important kind of prediction that light is bent by the gravitational field. That was completely not part of the discussion, so there was no evidence, nobody had any idea about that, and then general relativity predicts this bending of light by means of the gravitational field, and that was then actually verified experimentally. So that I already mentioned that, so when you go to gravitation from Newton to Einstein, the model is more complex. So there is an idea in physics that we want to have simple or parsimonious models, right? So we tend to prefer, as humans, as scientists, models, explanations that are as simple as possible. But we have to accept more complexity when needed, right? So I will not cite the sentence attributed to Einstein, who apparently he never said, but let's say this is related a little bit to the Occam razor. That again, Occam never stated in the way it is typically stated. The general idea is that we tend to prefer everything else being equal, the model that has the minimum, the least number of assumptions and therefore the simplest in this sense. Also in physics, we typically make strong use of and we look for symmetries or breaking of symmetries, right? So invariances, conservation laws, so we look for conservation laws. And these aspects are what we expect in a kind of conceptual kind of discussion from physics-informed modeling. And therefore, when we say, okay, we do the machine learning, artificial intelligence, we learn from data, we still want to give some kind of, as I will say in a second, of priors to our model. So we just not explore all the possible models that we have, but those that have some physical some connection with physical expectations, right? So models are interpretable, generalizable, and so and parsimonious, simple. They include symmetries, invariances, and conservation laws, right? So this is what we mean by physics informed. Now, more when we kind of contextualize this, we then have probably it is worth thinking about then say the physics kind of informed could be compared to the data driven or purely data driven kind of approach, and to kind of even here systematize a little bit, let me try this kind of picture. So let's say that we want to look into a situation in which we have an increasing number of data at our disposal for a given system, for a given set of observations, and compared to situations in which we have more and more physics kind of knowledge of the system, right? So we would have here, so let's say small data, some data, big data, to use something that people have been using a lot. Then we say no idea, no physics. I have no idea how to model that. We have some idea, and we lots of physics. So basically, we know what governs the system, the phenomenon, and so in this scenario, this is a scenario of physics where we still need data, right? So we would have some PD partial differential equation or ordinary differential equation, and so the data are just the initial boundary conditions. So this is still data, right? We need observation in order to actually predict the system, the behavioral system, our phenomenon, and so on. Possibly the coefficients of the equations, right? So there is some viscosity, there is some other parameter of the system that is there from data, or we would need other equations to find them. So the scenario in which we have very small data, we don't have really a scenario with zero data, right? So we have a partial differential or ordinary differential equation, which we still need initial boundary conditions to determine them, and or the coefficients of the equation. So I mean, the initial and boundary condition are always there, and depending on the kind of problem, we will need to infer from data the coefficients of the equation itself. So the parameters in general, not necessarily, it's not linear coefficients, parameters. Now the kind of opposite ends is the kind of big data regime in which we just model with data, right? So we don't have an assumption on the physics, and we do learning, and this has been some kind of, it is still a very rich field, and then we might be interested in the scenario in which we have some physical idea, we have a decent number of data points, and we want to make the best use of both. So we definitely do not have a huge amount of data so that we can just forget about physics and let the model do it for us. Of course, in a non-transparent way, then probably. And then we don't have the scenario in which we know all the physics, so we just need to fix a few parameters in order to make the prediction. So this would be the kind of regime of the physics informed machine learning, or AI, right? More. So now that we have tried to systematize a little bit what we at least expect, if not mean, by physics-informed machine learning, let me say that we can envisage kind of this physics-informed intervention on the modeling, on the machine learning kind of modeling and learning at different levels, right? So we try to enforce priors. Well, enforcing physical priors. Well, I use this unfamiliar word for physicists that is a prior, so this is from statistics, typically Bayesian statistics, in which you say, okay, I'm not really giving a rule that cannot be broken, I'm giving an initial guess. So this is a prior in Bayesian statistics, and then I have a kind of machinery to check how much my guess makes sense with the data, right? So, well, okay, as usual, there is a kind of zeroth kind of aspect in which we use the physics information, knowledge, to define the problem, formulation. So we have data, and we already use our physical kind of knowledge and intuition to frame which problem could be interesting, right? So we have data that are very heterogeneous, and we have to make a question to be answered by some modeling that has some kind of physical relevance, right? So this would be in the formulation of the problem, we impose a physical prior, so we don't just ask anything with respect to anything else, but we are guided by our physical intuition that, of course, is built on knowledge and culture. So, but more in practice, I mean, this is a kind of almost unseen prior, is on the data side. So collecting and curating data. So at this level, we can impose physical priors, right? In the sense that, so the curation part means essentially what we do to the data from the kind of storage situation to the representation that we give to a model that it is actually learning how to predict a certain observation, set of observations, right? So the preparation of the data, if you want, and then this curation of the data could and typically includes kind of physical priors, in the sense that, let's say, we construct a representation that is includes invariances. So sometimes a bit easier, sometimes less easy, but so, you know, the rotational, translational invariance we have seen a lot. We're talking about the machine learning potentials, interaction potentials that one tends to not just give coordinates and atomic species, but some rotation and most importantly permutation invariant representation with respect to the atoms of the same species. So we don't let the system discover these invariances, right? So it could be already at the level of this curation of the data or construction of the descriptor is the level in which we enforce physics priors, and then the other, so the aspects that are now typically what people talk a lot about when saying physical informed machine learning is the architecture so when you say architecture, one has in mind deep learning typically. So architecture is kind of number of layers and number of nodes per layer, or more some kind of construction of convolutional layers, so not just fully connected layers and so on. So this would be the architecture in deep learning, but in general it would be our model class, right? Okay, I can write it here. So we look at model classes that have some kind of embedding of the physical priors that we would like to have. And even more kind of the hottest kind of subtopic here is the definition of loss function. So as we show probably next time, there is a lot of activity in defining loss functions that embed the physical so physical aspect that we want, that we wish, and also, well, this is more like a transfer learning, right? To transfer of knowledge. It is the fact that selection of optimization algorithm. So basically, it has been realized that some optimization problems in machine learning, statistical learning, actually can be recast in optimization problem that we have in, well, say statistical physics, statistical mechanics, and we basically borrow refined optimization algorithms from statistical computational statistical mechanics. So it's probably not full-fledged kind of physical prior. Is more like borrowing things that we have already developed somewhere else. But yeah, it is sometimes mentioned as a physical informed. So having a smart optimization algorithm is sometimes also referred to as a physical informed machine learning kind of strategy. So let me just close with one quick example as a kind of teaser, and then I will show a couple more examples next time at this point, so they would require so like 15-20 minutes or so. So let me go to one example in which we basically kind of are in between the choice of an architecture that embeds some physical priors and the definition of a loss function. So definitely we are defining a loss function that includes this physical prior. So, and basically we are in the situation, so I'm taking this from a seminal paper on so-called physically informed, so you see again this PI, neural networks, the pins. So the kind of main person here, so there is a seminal paper from 2008 2018 or something. So the guy is Karnadiakis, something like 2018, I think. This is the example that I'm showing, and then there are many other kind of related works from the same person and group, and many other groups. So this physical informed neural network, they have the idea that one construct a network and a loss function so that you embed some physical knowledge, right? So the original example was a so-called viscose Berger equation. So something in fluidodynamics models, say, for example, shock waves in fluids. And so one has to solve a nonlinear differential equation where we are measuring, say, a field of, for example, well, some observable. So here will be the velocities, and so let me write the equation quickly. Eta second derivative, velocity with respect to position square. So the important thing is that we have observations. So we have these positions at times, and we have velocities measured in some way. And we know the equation governing so there would be an equal here sign, sorry. And then so this is the viscosity, right? Okay, it doesn't fully matter. It's just to show how we go from the knowledge that there is something that binds together input and observation variables, so x, t, and u, but it is a nonlinear partial differential equation. So we know the physics, but we don't know the solution. So we don't know u as a function of x and t. So this is what we want to model. And to do that, we resort to a modeling where we define a loss function, where we have a loss function that only takes care of the data, and a part of the loss function that takes care of the partial differential equation. So what does it mean? So the part, and that is something that weights the two parts. So the data means so that we have our mu as predicted with the model that we are training. So it depends on the model. So let me put it as the parameter of the model. And then we have the observations. So ui's, right? The i's, and then we are. And then we want to minimize the reconstruction error. PDE means that we want this to obey, the model should obey the partial differential equation. And so basically we say, okay, we are predicting, we have a model that predicts u. We can take derivatives, right? So we look at the u here, and we can take derivatives with respect to the time and positions, and then we say that this thing here should be as close as possible to zero, right? So 0 if the equation is fully satisfied, and is close to zero otherwise. And so we construct, so I should have somewhere the architecture here. The other one is for the next time. Oops. So this is an example of how we have this kind of physical informed neural network, right? So we train a neural network here. Let me make it a bit bigger. Where we learn the u's from the x and t, right? So we are given a set of x and t, and the use, and we just train a network that predicts use as a function of x and t. But then we can backpropagate the derivatives, right? So basically we can take the derivatives of this with respect to the weights and so on, and the activation, and go back and have the derivative with respect to x and t, and why not the second derivatives. So we can evaluate, because this is a kind of symbolic expression, as complex as is these derivatives, and we enforce that at the same time the reconstruction error and this expression here are as small as possible, right? So basically we put them together and then we minimize. So this is the big idea of physical informed machine learning when we construct networks and model classes and loss function that embed this idea of physical constraints. So I will come back to this at the beginning of next lecture. But for today, that's it. Thank you for your attention.